Hi everyone, so today we are going to be talking about rolling. So we also call this rolling without slipping, and that just means that if we're accelerating and we have wheels that are rolling on the ground, so that means they have both rotational motion, just going around like this, and translational motion. Without slipping just means that we might have a friction force if we're accelerating. We'll talk about that later. Or if we're not accelerating, we actually don't have a friction force. But what this means is that the wheels are not slipping in place. Okay, pretty self-explanatory. So here we have a wheel. It's translating and rotating at the same time, which is what rolling is. And of course, we have seen this equation before. Our S, which is the arc length right here, also the distance traveled when we're looking at a certain time period here, is going to be equal to that angle that we go through times R, which is the radius. And of course, if you are using this equation, you do have to be in radians in your calculator. So be very, very careful about that. Now, what we do here is we can differentiate this equation with respect to time in order to get a velocity equation for the center of mass of the object. And of course, you have seen this, again, you've seen this equation before, right? Velocity of the center of mass is going to be equal to omega, which is our angular velocity times the radius. So this isn't a new equation here, but here, instead of talking about the velocity of a point of that wheel as it just rotates, now we're talking about the velocity of the center of mass, and you actually get the same equation. So it makes it very easy to remember. So V here is the speed of the center of mass. Omega is the angular speed about the center of mass. And that's going to be the same for someone that's observing it from the outside and someone that's, say, riding this bicycle. They'll observe the same angular speed. So rolling here, like I was saying before, is simply a combination of rotational and translational motion. So pure rotation is when something is just rotating in place like this. Pure translation is when something is actually translating in space. And then together, when we put them together, we get rotation and translation together, which is our rolling motion. The interesting thing here is that we can look at the different velocities. And of course, center of mass here is not moving, but here we have velocity is equal to a positive velocity of the center of mass. Here we get a negative velocity of the center of mass, so together they're just zero. Pure translation, they're all moving together, so that velocity is going to be equal to the center of mass. This will also be equal to the center of mass, and then the velocity of the center of mass. We add those things together and we end up getting this thing right here. Now, what ends up happening here, which is very interesting, is that when the wheel actually touches the ground, we have a velocity of 0. And if we look at a picture here, and I'll get to that next picture soon, but we have, of course, a velocity of the center of mass, and then the top of that wheel actually ends up being 2 times the velocity of the center of mass. And we can see that in a picture like this. If you take a snapshot of a bicycle wheel as it is rolling, you can see that we're kind of stopped down here as this wheel touches the ground. We have a velocity of the center of mass as this thing is rolling, and then the top is all blurred out because that part is going the fastest, which is very, very interesting. Now, another way that we can think of this is we can kind of think of rolling as a form of pure rotation if we have an axis that extends through the point where the wheel connects to the street as it moves. Meaning, instead of thinking about this as rolling motion, like rotation and translation, we can think of this point as it connects to the street, and we are rotating about this point like so. All right, so that's what this is trying to say. This is our rotation axis here. And here we can see that we have a velocity of the center of mass, and this is going to be 2 times the velocity of the center of mass. So what we do here is we consider the rolling motion to be pure rotation about that axis passing through point P, which is the point that's touching the floor down there, and perpendicular to the plane in the figure. And those vectors that are drawn on this figure show the instantaneous velocities of selected points. Now, the angular speed omega that a stationary observer assigns to the wheel is the same angular angular velocity that the rider assigns to the wheel as they observe it, like I said before. And then here what we get, let me take that away so you can actually see it, is we end up getting that the velocity at the very top of this wheel right here is going to be that angular velocity times the radius, where the radius is the distance from the axis of rotation to that point where we're measuring the velocity. So here what we get is actually 2r, because of course we're talking about r as in the radius of the wheel. So 2 times r here, and then we're just kind of rearranging this right here, sorry. So it becomes 2 omega times r, and of course omega times r is just the velocity of the center of mass. So we get that the velocity of this point at the very top of this wheel is going to be 2 times the velocity of the center of mass. So this is basically just proving the figure that we had before, which told us that this velocity, linear velocity at the top point right here, is going to be 2 times the velocity of the center of mass. And then of course, this is a velocity of 0 where it actually touches the ground. Now, the reason we do this is because we already know a lot about pure rotation. So thinking of rolling as pure rotation, we can then get a few other equations that we can then use with our rolling motion. So another one of those equations is the kinetic energy of rolling. So again, if we view rolling as pure rotation about an axis through point P, we know that the kinetic energy of something that is rotating is 1/2 times the I, which is our moment of inertia, or rotational inertia, times omega squared. And of course, this is going to be our I, our moment of inertia through point P. So if we're talking about, say, a wheel, it's not going to be just 1/2 mr squared, because it's a parallel axis, right? It's not through the center of mass. So from the parallel axis theorem, we get that the rotational inertia through point P is going to be equal to the rotational inertia through the center of mass plus the mr squared, which of course is how, we use this parallel axis theorem. We're adding that mh squared, which is what I told you before, but of course h here is the radius, because that's that perpendicular distance between the axis through the center of mass and the axis through that point P. So what we end up getting here is we're going to now substitute this whole thing in for our our rotational inertia in the kinetic energy equation. And so we get this. And then what we're going to do here is distribute this omega squared. So when we distribute omega squared, we get 1/2 times I, our rotational inertia through the center of mass, times the angular velocity squared. And so this right here is the kinetic energy of rotation through the center of mass. And then right here we get plus 1/2 mr squared omega squared. But we know that omega times r is just linear velocity. So what we end up getting here is just linear velocity squared. And this is starting to look very familiar, right? Because look, we have kinetic energy is equal to the rotational kinetic energy plus translational kinetic energy. So when we have something that's rolling, it has both rotational kinetic energy and translational kinetic energy. So we get, when we derive this through thinking of this as pure rotation about that axis through point P, we get something that makes a lot of sense, because again, when something is rolling, it's both rotating and translating, which is why we have both rotational kinetic energy and translational kinetic energy. Now let's talk about forces of rolling. So if the wheel rolls at constant speed, it doesn't have a tendency to slide at any point of contact when it touches the ground. So the interesting thing is that no frictional force actually acts there. Again, though, the main point of this is that if the wheel is rolling at constant speed. So that means our angular velocity is constant, our linear velocity is constant, okay? It's not accelerating at all, linearly and angularly, all right? So because it's not accelerating, there's no frictional forces acting at the point of contact. If a net force acts on the rolling wheel to speed it up or slow it down, so therefore we have a tangential acceleration, a linear acceleration, we also have an angular acceleration, then that net force is causing an acceleration of the center of mass along the direction of travel, and it then causes the wheel to rotate faster or slower, and that in turn causes an angular acceleration, like I was saying. So when we have this acceleration, that then tends to make the wheel slide at point P. So then we have a frictional force that has to be present to oppose that tendency. Okay, so we only have frictional forces acting on this wheel, causing it to rotate, acting on the wheel at where the wheel is making contact with the ground when we have an acceleration. So when someone that's in a car is pressing on the gas pedal or pressing on, the brake pedal, but then of course we're trying to stop that rotation. But if we're pressing on the gas pedal, we're trying to we're causing a force that's causing our car to speed up, which then we have to have a frictional force in order to get those wheels to speed up. So what's happening here is that if we're trying to speed this thing up, it will tend to slide at the bottom there. Now the direction of the friction force is very interesting, and I'll talk about that on the next slide. So if the wheel doesn't slide, the frictional force is a static friction force, because again, remember the velocity where it touches the ground here, as it's rotating, as it's rolling across the ground, the velocity as it touches the ground where it's in contact, that is 0. So when it touches the ground, it's not sliding along the ground. So because it's not sliding along the ground, it's actually a static friction force. And we call this motion smooth rolling. Now, what I want you to think about is the direction of friction. So if we have an acceleration, what's happening is this wheel is trying to speed up. Okay, it's speeding up like this. So if it's trying to speed up, the bottom of the wheel wants to go this way on the ground, like that. Now, if the bottom of the wheel wants to go this way and the wheel is moving this way, so the bottom of the wheel goes this way, we know that friction opposes the motion or the intended motion. So if the tendency of this wheel, like think about a car that's stuck in mud or something like that, and you're pressing the gas pedal, trying to get it to go, those wheels are spinning out, right? Like this. And again, they're tending to go this way. So because they're going this way, that friction force has to oppose the motion. And that opposing motion is actually in the direction of motion, which is very, very interesting. So if we look at a picture of this, we have this wheel is rotating like this, and the wheel is translating this way. So if we're trying to accelerate it this way, the bottom is tending to slide in this direction because it's going clockwise. So the bottom's tending to slide to the left. So the friction force is actually to the right, which is in the direction of the motion, which is very, very interesting. So this is the direction of our static friction force when we have an acceleration. And remember, we have a linear acceleration of the center of mass. We also have an angular acceleration of the wheels because we're trying to speed that thing up. So the friction force is only present, again, when we actually are speeding up or slowing down, not when we're going at a constant velocity. There is actually no friction present when the wheels are going at a constant velocity.